Hey guys, so I wanted to do a couple of examples with you on your potential energy diagram activity today because I know these can be a little bit tricky. I've already linked another video to YouTube. I think this girl's name is Miss Maribel. She is awesome. She has a lot of videos on her channel where she does chemistry, reviews, all kinds of topics. So if you're still a little confused, make sure you watch that. And then, of course, I'm recording the video that will go right here with the actual assignment. So we're going to make a copy as always. And this activity is only 4 different slides. So there's 4 slides, and it is a drag and drop activity where you're going to label the potential energy diagrams. And you're going to determine whether or not each of the reactions that are taking place are exothermic or endothermic. So we've got definitions on slide 2 just to give you a refresher of everything. This is not, you don't have to do anything with this slide. It just gives you the background information. Remember, these 2 things are very important. So bonds are forming when energy is released. So when the slope goes down, that's when our bonds are going to form. And then it requires energy to break bonds. So if you see a slope going up, that's going to indicate that energy is going up, breaking those chemical bonds because the energy is being absorbed. Okay. And then of course it's endothermic if the delta H is positive, and it is exothermic if the delta H is negative. So that's what we have to keep in mind. So I'm going to do the first one with you guys, and then you guys are going to do the last 3, but I will point out some things in 5 and 6 because it can be, or I should say 3 and 4 because it'll be a little bit tricky. Okay, so here we have all of our drag and drop. So that's the first part. We have to drag and drop. And then we have to determine whether or not it is endothermic or exothermic. And we'll talk a little bit about that at the end. Okay, well, first let's start with the easy stuff. We know that our reactants go into the reaction, right? So we start with reactants and we end with our products. Okay, so that's always start with reactants, end with our products. Our activated complex is that kind of intermediate as we get about like halfway through our reaction. It's that intermediate complex that's going to go right in the middle here at this peak. Okay. Now we have to determine where are the bonds forming and the bonds breaking. Well, remember, when we're breaking bonds, it takes energy, right? So the energy of the reaction is going to be increasing when our bonds are breaking, and they're going to be decreasing when our bonds are forming because it takes energy to break a bond, and then energy is released when bonds are formed. So in this instance, remember, this is our potential energy on our Y, and the progress of our reaction is on our X. So what we're seeing here is basically just the formation of these products and how the energy, the heat energy, is changing. So the bonds are forming when there is a downward slope, and the bonds are breaking when there is an upward slope. Okay, so now we have our labeled diagram with our different points of the reaction. So the reactants go in. Energy is absorbed to break the chemical bonds. The activated complex is the intermediate. And then we have our bonds being formed. That energy is being released. And then we have our products. Okay? Now remember, our activation energy is the energy from the start of the reaction up to basically the activated complex, so where the reaction really gets going. So that's going to be around here. Okay, I think that's okay. I think I can leave it right around here. And basically the activation energy is just the point of the reactants up to the activated complex. Okay. Now our delta H is our change in enthalpy. And I'm going to put this guy right around here. The change in the delta H is going to be the difference between the reactants and the products, right? So our products minus our energy of reactants. So the difference between here and here. That's why I'm putting him here, just because you can see it a little bit where it's the difference between the reactants and the products. Okay. Now, here is our fully labeled diagram. Now, what do we have to do to figure out if this is endothermic or exothermic? We have to look at where our products are ending, okay? The energy of our products. Here, the energy of our products are lower than the energy of our reactants, okay? So the energy of our product is lower than the energy of our reactant. So I know that this is going to be exothermic, okay? If this product line, so if the product line was above the reactant, it would be endothermic, because that would mean that the energy of the product was higher than the energy of the reactants. But since it's below, it's exothermic. Now, you could also do that because we know this is the energy on the left-hand side. You could make up just like random values and check yourself, because remember, we know in an exothermic reaction, the delta H is negative. So if we're looking at our energy, let's just say this is energy from 0 to 10. Okay, so 0 to 10. So if this was, our y-axis was 0 to 10, our products would be around a 2, and our reactants would be around a 5. So 2 minus 5 would be negative 3. That's a negative value. Yeah, our delta H is negative, so this is exothermic. Okay, so you can check yourself that way, or you can just look at the position on the table or on the diagram. Okay, so that's what you're doing. The second one is the same exact way, although if you look, your energy of your products is going to be a little bit different than your energy of reaction, so make sure when you're talking about whether this is endothermic or exothermic. And then 5 and 6 will be a little bit of a challenge for you, because if you notice, there is no kind of climax or bump in the diagram. So like 1 and 2 has a very clearly defined bump, and then 5 and 6, they do not. And the reason for this is because there's no activation energy needed here. Okay, the reaction is already in progress, so that's why we're not seeing that. So just be aware that on the last 2 slides, you are not going to use the activation energy. Okay, there's no activation energy because what we're seeing is basically a spontaneous reaction that doesn't need energy to get started. So we're not going to have activation energy on the last 2. Okay, you're not going to have activation energy. You will have delta H. You will have your reactants, your products. You will have your activated complex that is still somewhere around the middle. And now for these last 2, one of them will have bonds forming and one of them will have bonds breaking. But these 5 and 6 slides, they won't have both. Okay, so remember to look at the slope, whether it's going down or upwards, to determine whether those bonds are forming or whether those bonds are breaking. Okay, it's a little bit of a challenge, but I know you guys can do it. And then, of course, for your endothermic and exothermic for these, still same thing. Pay attention to where your energy of your products and reactants are in relation to each other. Remember, if the change is negative, it's exothermic. So if the energy of the products is below the reactants, is exothermic. If it's positive and the energy of the products are above the reactants, then it's endothermic. I encourage you to, again, watch that second video that's linked in your assignment, but if you're still having some confusion, please let me know.